Stainless steels today serve our daily needs in 1,001 different ways, even though at times we may only be subconsciously aware of it. If we turn back the pages of time to a date in 1934, the story of Firth Vickers begins. The special steels produced by our parent companies in the form of ingots are shaped by forging or rolling into the bars, plates, sheets and strip, which are the finished products of this company and the raw material for the engineers of many industries. It is often not appreciated that, with a few exceptions, over 40 different types of corrosion and heat-resisting steels are produced in these forms. Sheet production commences with the forged or rolled slab, which has been dressed by grinding before rolling to an intermediate stage known as a mold. This is done in a hot reversing mill. Molds are carefully inspected and surface defects removed before hot sheet rolling, which is carried out on a number of two-high pullover mills. As the sheet is being rolled, it's necessary to return it to the furnace for reheating, because rolling can only take place between a critical temperature range. The larger mills, where thicker and heavier sheets are rolled, are fitted with power-operated manipulators. After hot rolling, the sheets are softened and cleaned by pickling prior to cold rolling to final gauges on four-high mills. This is followed by a final softening treatment in vertical gas-fired furnaces to a strictly controlled time cycle according to the type of steel, and rapid air cooling. Sheets are then descaled by acid pickling, and all traces of scale are removed by swabbing and washing thoroughly in water before passing through to the warehouse for inspection, flattening, and shearing to size. Sheets can, of course, be supplied with a cold rolled finish, lightly planished or alternatively in the hard condition, depending on the customer's requirements. Sheets up to 40 inches wide and strip in coil are produced by continuous production methods and will be seen later in the film. Bar production ranges from 6 inches to 1/4 of an inch diameter, as well as many other sections such as squares, hexagons, flats and angles in a wide range of sizes, which are supplied descaled, smooth ground or cold drawn. Billets are carefully dressed to make certain they're free from surface defects. And at each stage in rolling, when the steel is cold, further careful inspection and dressing is carried out before the bar is rolled to the finished section and size. After hot rolling, bars have to be heat treated to produce the required mechanical and physical properties in a battery of gas-fired furnaces designed to provide accurate temperature control over a wide range of conditions. Before dispatch, all bars are straightened and inspected. For certain applications, bars are tested by the Magnaflux crack detection technique. An important function of the warehouse is the correct identification and color coding of the many different types of stainless steel produced. Wire and wire products absorb large quantities of stainless steel every year, and we supply the 1/4 of an inch diameter coiled rod to the wire drawers for subsequent hot and cold reduction. The fast mill producing this rod is always a highlight of any visit to these works, and a high degree of skill and teamwork can readily be appreciated. Castings of all types in stainless and heat-resisting steels are made in our foundries. For the production of centrifugal and centri-die cast rings in these special steels, steel molds or dies are fitted to the spinning machines, mounted either vertically in a casting pit or horizontally, depending on the diameter of the ring. The steels are melted in high-frequency electric furnaces, which are particularly suitable for these highly alloyed steels to ensure the highest degree of cleanness and purity. Very strict parametric control is essential during the teaming and casting operations. The technique of centrifugal and centri-die casting of these special steels was pioneered by our company and has now been developed to include not only rings for the many types of gas turbine and turboprop aero engines, but for many other commercial purposes. The process has now been perfected to such an extent that rings up to 6 feet in diameter may be produced. The original technique of centrifugal casting was developed in connection with the manufacture of sleeve valves for the Bristol piston-type aero engines, and over 2 million have already been supplied. The steel is poured into a cast iron mold, spinning at 1100 revolutions per minute. All centri-spun castings are subsequently heat-treated in gas-fired furnaces under strict control to give the best mechanical and physical properties. Rings of more intricate shape are cast in refractory molds with sand cores, and these are mounted on the spinning machines in a similar manner to the steel molds. An idea of the wide variety of shapes can be gained from these rings being machined using carbide tools. As large numbers of centrifugal castings are used in the aircraft industry, they have to pass very rigid inspection and tests, involving examination by the magnaflux and ultrasonic flaw detection techniques, in addition to searching surface examination. Small and intricate components are made by the precision investment, or as it's better known, blast wax process. This centuries-old method of reproducing shapes has been developed and applied to stainless and heat-resisting steels. Small parts, which if made by other methods would involve costly machining operations, are made to very close tolerances and in most cases weigh only a few ounces. For each individual casting, a model is made by injecting wax into a metal die of the required shape. The accuracy of the finished casting depends on the accuracy of the wax model. Having removed the wax model from the die, each one is assembled to the casting runner, and the whole assembly is coated with investment to ensure a superfine, smooth finish to the final product. The assembly is then mounted and bonded with investing refractory, which is allowed to solidify and dry out. The mold is then heated to low temperature to remove the wax, and then preheated to 1050 degrees centigrade, ready for casting. Steel is melted in small electric furnaces, the hot mold fixed over the furnace aperture, and the whole assembly turned to allow the steel to flow into the mold. After solidification, the molds are broken and the castings heat-treated and removed from the runner by cutting with a high-speed friction bandsaw. Precision castings are in service in a great number of industries and have opened up a new field to the design engineer. The reorganization of our foundries in recent years has resulted in the increased production of this type of work and in a range of compositions and for a variety of service conditions which are unique. Mechanical methods of production have proved so successful that they have been extended to deal not only with large numbers of castings of relatively small weight, but also those of greater weight whenever quantities can be ordered. Castings which do not lend themselves to machine molding are floor molded individually. The preparation of molding materials, together with the steel melting in high-frequency electric furnaces, is all supervised by qualified and experienced staff. Bulk production of castings necessitates precise technical control at all stages, and pouring can only take place within a closely defined temperature range. It should be remembered that castings can be supplied in a wide range of our special steels, and so much depends on the correct choice of alloy that it is only by close collaboration with our customers that a decision can be reached regarding the best design and the best material to adopt for the specific purpose. The runners are removed from the castings and finishing operation completed before heat treatment, which is carried out in gas-fired furnaces to obtain the optimum corrosion-resisting and mechanical properties in the steels. Engineers familiar with foundry practice recognize that to achieve the highest standard of quality in production, the methods must be subject to the closest possible scientific control and be so designed that they can be applied to meet each and every problem as it arises. Everyone is familiar with the benefits achieved in medical science by the use of radiography, and it is interesting that the steelmaker has long applied these techniques in the metallurgical field, together with the more recent byproducts of the atomic age, by using radioactive isotopes to examine the internal structures of these special steels. We have the experience and the degree of specialization which is so essential in the production of high-quality stainless steel castings of all types. The period between the formation of the company and the start of the 1939-45 war was one of continuous development in the whole range of stainless and heat-resisting steels. During this time, the various techniques of manipulation and fabrication to an increasing variety of industries came to be understood by designers and engineers, creating a greater demand for these special steels. Towards the end of the war, it was clearly foreseen that the growing demand for stainless and heat-resisting steels would necessitate building an entirely new plant, capable of continuous production in bulk quantities. The first ground was broken in 1948, and this modern stainless steel producing unit is now in full production and is a subsidiary company called Shepcote Lane Rolling Mills Limited. Up to the present time, the common practice in this country has been to produce stainless steel sheets by the conventional pullover mills. But at Shepcote Lane, the new mills produce long coils of stainless steel strip up to 1 meter wide, which are subsequently sheared to individual sheets or strips. The two hot reversing mills are capable of reducing 5-inch thick slabs to a finished hot roll thickness of 0.140 inches. The strip is then coiled and trimmed, ready for softening and descaling prior to cold rolling. From the production point of view, plant has been designed to reduce handling to a minimum, as many of the processes as possible being automatically controlled through continuous line. Flash butt welding is used to weld the coils produced in the hot mills together for economical cold rolling. For softening and descaling, 5-ton coils are tack welded together to form a continuous loop to pass through the furnaces and pickling tanks. Earlier in the film, the softening and descaling of individual sheets was shown. It should be remembered that the same attention to the treatment of different types of steel must be exercised, even though the process is continuous. The temperature, soaking time, and the period of immersion in various acid solutions all have to be taken into consideration. The steels are further worked by cold rolling to produce a superfine, smooth finish and to reduce the thickness to the final gauge as ordered by the customer. For this purpose, two entirely different types of rolling mill are employed, the first being a 4-high mill capable of making reductions of 60% on the thickness. The second is the Sensomere or cluster type of mill with very small diameter work rolls, only 2 1/8 inches in diameter. The arrangement of the backup rolls can be clearly seen. One of the essential virtues of this type of mill is its ability to roll stainless steels, which in some cases are not easy to reduce without intermediate annealing, with a great degree of accuracy. After cold rolling, the strip is again passed through the softening and descaling lines. The first of these lines has already been seen, dealing with strip in the hot-rolled condition. The second and third lines are used for cold-rolled strip, which requires an intermediate softening, and also for those coils which have been reduced to the finished gauge. In many cases, the coils are rolled as thin as 1/100th of an inch, and therefore as many as 3 cycles of cold rolling, softening, and descaling may be necessary before the final gauge is reached. Final surface finish is produced on this 2-high skin pass mill. It will be seen that coils are interleaved with paper to minimize the risk of scratching. In our warehouse, the finished coils from the mills are stacked prior to cutting into sheets and strip. Sheets, 14 gauge and thinner, can be cut from the coil to any standard size up to 11 feet long by 40 inches wide. Alternatively, any shape of blank, whether square, rectangle, or circle, can be supplied. And in some industries, there is a growing tendency to utilize edge-trimmed coils between 36 to 40 inches wide, up to 5 tons in weight. Here again, the plant has been designed to reduce handling to a minimum. Coils for strip production are most carefully examined for surface imperfections prior to slitting to an almost limitless range of widths. Thinner gauge strip, less than 10 inches wide, is produced by further cold rolling on these narrow mills and is supplied in either coil or in cut lengths. Many items of industrial plant and domestic equipment fabricated from Staybrite stainless steel are required to have a polished finish for reasons other than just appearance. In the brewing, dairy, and catering industries, for example, hygiene and ease of cleansing are of major importance. A considerable proportion of the sheets supplied by our company is therefore provided with a polished finish on one or both sides. Over 70 polishing machines of various types are in use, some being fitted with abrasive belts and others with the older type of mop, according to the particular operation which achieves the final polish. This may be a dull finish or a bright mirror polish, with various intermediate degrees to meet both special and standard requirements. Before packing, the sheets are passed through a continuous degreasing plant to remove all traces of grease and polishing lubricants, then inspected and shared to size. Each individual sheet is labelled with the type of stainless steel and the size and thickness. With sheets having such a high degree of finish, extreme care is taken in packing so that the goods reach the customer in perfect condition. It will have been seen during this tour of the works that it is our aim for the products to be of the highest quality and workmanship, and every possible care is taken at all stages of manufacture. It is also our desire that these special steels should be of the most suitable type for the working conditions involved. From the earliest days of the development and production in our works of stainless and Staybrite steels, we have endeavored to maintain a policy of close cooperation and exchange of technical information with users and prospective users of these steels. The experience thus gained over the years, together with continuous research and development which takes place in our own laboratories and works, enables us to offer a unique service of guidance in the selection and use of suitable materials. A knowledge of all the facts, coupled with a mutual understanding of the problems, is of such importance that at all times we welcome and encourage every opportunity for discussion regarding the use of our corrosion and heat-resisting steels.
Familiar everyday objects. Objects so familiar that it's easy to forget how important they are to us. Making our daily life better, easier and more smooth running. Objects that are attractive, functional, hard-wearing and everlasting. Objects made from stainless steel. But what lies behind a small sugar pot like this? The answer? A high-technology industry that melts together raw material and scraps stainless steel, recycling old steel into new steel, reforming a bright, shining surface that, unlike ordinary steel, will stay bright forever, making it ideal for many applications in everyday life. Let's see what makes stainless steel different from other steels. Everyone knows that ordinary steel can go rusty, but all stainless steels contain some of this, a metal called chromium. Over 70% of stainless steels also contain this, another metal called nickel, and these two metals don't rust. This bumper is made from ordinary steel. It hasn't rusted because its surface is protected by both a thick layer of nickel and a thinner top layer of chromium. Unfortunately, if these surface layers are damaged, then the steel goes rusty. This stainless steel sink also depends on chromium and nickel for its corrosion resistance. This time, they're not just on the surface, they're an integral part of the steel. So scratching it merely exposes a new surface, and the protection reforms. Metallurgists have studied the way that this works using modern scientific instruments. The surface of this piece of steel, for example, can be magnified up to 300,000 times in this microscope. It uses beams of electrons instead of light to obtain a picture of the surface.
We all know that the Earth's atmosphere contains oxygen, and most metals react with oxygen to form a film of oxide. Because ordinary steels contain about 98% of iron, this surface film is iron oxide. Unfortunately, it's porous. More oxygen passes through it. More iron oxide forms to build a layer of what we call rust. Chromium also forms an oxide, but this time it's not porous. It's also so thin that you can see the bright surface of the chromium through it. Now, when you put enough chromium into ordinary steel, it makes its oxide behave in a similar way, and a thin, protective, passive film is formed that stops any further corrosion. Also, if you remove the passive film, then the bare stainless steel reacts with oxygen to form a new one, so it's self-repairing, and the resistance to corrosion continues.
Very often, stainless steel is exposed to